Welcome to the Truss Bridge tutorial. It is recommended that the viewer pause the program shortly to copy down the problem so that they can see the problem as it was given as the tutorial progresses. The following tutorial will help you solve simple truss problems to determine the force in each member of the loaded truss. Before us we have a simple truss with joints A through F, one member diagonally between joints B and E, and two loads, one load of 4 kilonewtons at joint F and another load at 6 kilonewtons at joint E. Joint A is on a roller while joint D is fixed to the ground. Before we start, it's important to establish how to label all the trusses. Between each two joints, we label the member with the corresponding joints. For example, between joints A and B is the member AB, while between joints B and C is the member BC. Also, while the bridge is being pulled down by the 4 kilonewton load and the 6 kilonewton load, it is also being pushed up at joint A and joint D by the ground. At this point, it is important to stop and take a moment to discuss tension and compression. Each member can undergo compression, or a squeezing force, or tension, a stretching force. In addition, the joints can also undergo tension and compression. Each joint will always feel the opposite effect that the member feels. If we look at joint A, we can see that the joint is being compressed by member AB. Therefore, the member AB is actually undergoing tension. They will always experience an opposite force. It takes some investigation of the joints to completely understand this process. Before we can start solving for the force in each member of the loaded truss, we need to understand the three rules of statics. One is that the sum of all forces in the x direction is equal to 0, which basically means left equals right. The sum of all forces in the y direction equals 0, which means that all the up forces equal to downs. And the sum of all the torques is also equal to 0, which means that any torque going in a clockwise direction will equal all the torques going in the counterclockwise direction. In this problem, we won't be needing left equals right, but we see that there are two loads, the 4 kilonewtons and the 6 kilonewtons pulling down. Therefore, there will be forces pushing up at joints A and D to fight off those two forces. We're going to solve for those forces first, and we're going to do it by using rules 2 and rules 3. Torque is defined as force times distance from an axis or a turning point. For example, in the diagram we see that there's a bar with an origin, and the bar is 2 meters long, and there's a 6 Newton force pulling down at the end of the bar. To calculate the torque, you just simply take the force of the 6 newtons times the distance that 6 newtons is from the pivot point, and you simply multiply and you get negative 12 newtons or Newton meters. That's going in a clockwise fashion, therefore we call it negative. There's really no need to get too carried away with the negatives and positives. All you need to keep track of is which torques are going counterclockwise and which torques are going clockwise, and then set them equal to each other. And we'll see that coming up in the panels following this one. In this step, we're trying to determine force 1. That's the force pushing up at joint A. We'll later figure out force 2 over at joint D. What we're going to do is we're going to put the pivot point right on joint D. That way force 2 goes straight through the pivot point, because the distance then becomes 0 for force number 2, and that force essentially goes away. So then what we have is we have force 1 going up, or more appropriately clockwise. We have the 4 kilonewton force going counterclockwise and the 6 kilonewton force going counterclockwise as well. So what we're going to do is we're going to set our clockwise torques equal to our counterclockwise torques. So F1 times the 12 meters, that's force times distance in the clockwise direction, is equal to the 4 kilonewton force times 9 meters, that's the counterclockwise direction, plus the 6 kilonewton force times the 3 meters, that's the second counterclockwise direction. So do a little math, divide by 12, and you get F1 is equal to 4.5 kilonewtons. Now that we figured out that F1 is equal to 4.5 kilonewtons up, we can now use the sum of all forces in the y direction equals 0 to finish this off. That's simply up equals down. We know that the 4.5 kilonewton force goes up. We know that F2 also goes up. and we just set that equal to our down forces, which is 4 kilonewtons and 6 kilonewtons. You can do what we did in the last step, and you can set the pivot point on joint A, and you can do this using the sum of all torques, the clockwise equaling the counterclockwise, but it's a lot easier to just do up equals down, as you can see from the math that follows. So 4.5 plus F2 is equal to 10 kilonewtons, and just subtract and you get F2 equals 5.5 kilonewtons up. So now we've solved for both of our up forces at the two spots where our bridge touches the ground. Now we can start solving for the forces in the members. One last thing to do before we solve for all the forces in the members is just to figure out what all the angles are in the truss system. It's nothing particularly complicated. You can solve for angle theta 1 just using tangent, and you get 53.13. Simply subtract 90 minus theta 1 and you get theta 2 of 36.87, and do kind of the same process throughout the truss system and you get some of the other angles. Notice that all the angles on the left are symmetrical with all the angles on the right, and so there's really no need to solve for all the angles on the right. You already know the answers. Now that we've solved for F1 and F2 and we've solved for all the angles, we can finally solve for all of the forces in our members. We're starting with joint A because there's not very many members that go into joint A, and we can solve for all the members in joint A with only one piece of information, the 4.5 kilonewton force up and the angle, 53.13. We could start with joint D just as easily. In joint A, the up forces have to equal the down forces, so the y component of member AB has to equal 4.5. So 4.5 equals member AB times sine of 53.13, and member AB is equal to 5.625 kilonewtons. From this point forward, we're going to be taking off kilonewtons. We'll bring them back at the end. It just makes the math easier to read. Now we also know that the x component of AB is equal to AF, so that the left force on that joint equals the right force on that joint because the joint is not accelerating. So AF equals AB cosine of 53.13, and member AF equals 3.375. After solving for joint A, we'll go on ahead and solve over on joint F. So joint F, we know that we have 4 down. That came from the original diagram. It told us in the problem that there was a force of 4 kilonewtons down at joint F. And we know what the force in AF is because we just solved for it. So this is very easy. Because there's only one up and one down, there's no angles or anything, we know that BF is equal to 4 because up equals down. Same for left and right, we know that EF is equal to AF. And so EF is 3.375. Once you've solved for one side of a member, the other side of the member has the exact same force. So now we can use these members to solve over on joint B and on joint E. That's one of the great things about the static problems, is that the force remains the same throughout the joint. So once you have it at one end, you have it at the other. Next we'll go and solve joint D. We could have solved joint D from the very beginning, but you gotta just pick something that you want to solve first, so we can solve it now. I won't go into a lot of discussion on that. It's solved in exactly the same way joint A is solved. Then selected as joint C, because there aren't very many members that go into joint C, and we already know what CD is because we solve it when we're solving for joint D. Because CD is an up vector, we know that CE has to be down, because if you're going to have an up, you got to have a down to counter it. And because CD is going to the left, we know that BC has to go to the right. That's how you determine which way to face these arrows when you're making your joints. Now that we've solved for all the joints that have not very many members going into them, we can solve for one of the more complicated ones, joint E. Joint E was saved purposefully as one of the later joints to analyze because there are 4 members going into that joint, which makes it more complicated. But before we even start joint E, we already know what CE, DE, and EF are because we solved them in earlier joints. So we're just going to redraw the force diagram on that joint. We don't know what BE is because we haven't solved joint B yet, but we put the other ones in. Now that we have the other ones, we can add forces. to find that the sum of the x forces is 0.75 to the right, and the sum of the y forces is 0.5 down. So we know the left and we know the right. You can use the Pythagorean theorem to figure out what BE is, and we find that it's 0.9 kilonewtons. There's no need to solve for joint B, because joint B is made up of members that we already solved for in other problems. It appears that the center joint, 0.9 T for tension, is actually under compression if you look at the arrows. What you have to remember that the arrows represent is how the member is acting on the joint. So for example, if you look at joint E, it looks like that center member BE, is compressed together, but really what it's doing is it's pulling on joint E. So according to Newton's third law, joint E is pulling back on the member. So the member is pulling the joint out of the socket, and the joint is pulling the member into the socket and is actually putting it under tension. Thank you for taking the time to listen to this brief tutorial on truss systems and how to determine the force in each member of the loaded truss.